Okay, let's continue on with this test. We're looking at number 7, part C. How much heat energy would it take to evaporate the water starting from 100 degrees C? So what did we just do? How much energy would it take to get the water to be steam at 100? Okay, so for this one we started at 20 and went all the way to steam. Now it's just asking starting at 100. So that would just be the heat of evaporation, Q evap, like we calculated there. So we've already got that number. It's just this, 4.55 megajoules. Yes. All right, so no extra calculations needed on that one. Part D. What is the total energy needed to evaporate all the water starting from 20 degrees? I feel like we just did that. What happened here? Alright, so it's kind of a messed up question. What is the total energy needed to evaporate all the water starting from 20 degrees? So that's what we just did. And so that is the 5.22 megajoules. So I'm not quite sure what I was thinking there. But we'll just go with this. Okay. How much power is needed to evaporate all of the water in 20 minutes? Okay, so power is work over time or energy over time. Oops. Bad eraser. Over time, or in this case, the energy is heat energy, so that's heat over time, and this will be the total heat. And so this is like just what we did before. So we got the 5.22 megajoules divided by 20 minutes, but we need it in seconds, so we're going to multiply by a fraction of 60 seconds is 1 minute, so we get 5.22 exponent 6 divided by 20 times 60. 4.35 10 to the third kilowatts. Okay. So this P is power, not pressure. Lots of P's. Okay, number 8. Consider a giant yet portable simple harmonic pendulum 9 meters long with a mass at the end weighing 10 kilograms. Assume the cable has no weight and we want a maximum velocity of 2 meters per second. So this is V max, this is M, and this is L. Alright, how far back should we pull the pendulum to get the desired maximum velocity? Alright, so we have our Vmax equation. Was A before, when we were doing the mass, it was square root of K over M, but here when we're doing a pendulum it's square root of G over L. And so we're asking how far back should we pull it, so that's A, right? So we want to solve for A. So A is going to be divide through by this, or flip over and multiply, so we got Vmax times the square root of L over G. Alright, Vmax is 2 meters per second, square root of L, 9 meters, and G, 9.81 meters per second. We'll assume we're on Earth here. So we're going to get an A here of 2 times square root 9 divided by 9.81. 1.916 meters, so A 1 9.92 meters. Alrighty. What is the maximum kinetic energy of the pendulum? So kinetic energy, we'll just do KE 1/2 mv squared, and we want the maximum, so we're do maximum velocity, which we just found, and so 1/2 m is 10 kilograms, and v, oh no, we didn't find v, we were given v. Yep, v max, that's it. Alright, so KE max is 5 times 4, 20 joules. Double check my stuff here. Where are we? Looks good. How long will it take the pendulum to make 5 full swings? So 5 full swings is 5 times 1 full swing. 1 full swing, or T is the time it takes to make 1 full swing. So to get 5, which is 5 times the period T. We've got a formula various different ways, but let's just go with it directly. T is 2 pi square root of L over G. It was, anyway, similar to the other one that we did for the mass, just different. Instead of L over G, we had M over K. So, substituting in, we know everything. L is 9 meters, G is 9.81 meters per second squared. So 2 times pi times square root 9 divided by 9.81, 6.018 seconds, but we want 5t, so take that times 5, 30.1 seconds. Okay. Part D. What is the frequency of the oscillation? Omega F is omega over 2 pi. Omega is the square root of G over L. It's from our equations. And so we got 1 over 2 pi square root of 9.81 meters per second squared over 9 meters. So frequency square root 9 divided by 9.81, that whole thing divided by 2, there's parentheses in here, divided by 2 times pi. Looks good. So the frequency is 0.152 hertz. What? Well, it should be 1 over the period. The period was 6.018. Let's try that. 1 divided by 6.018. 166. wrong here. So omega square root of L over G. We got 1 over all of this. Oh, square root of G over L. I did square root of L over G. Ah, okay. Let's try that again. So we got square root of 9.81 divided by 9, and then all of that divided by 2 times pi. There we go. 1.166. 0.166 hertz. Okay, that's better. Write an equation for the horizontal position of the pendulum. So remember x of t for all these simple harmonic motions. Simple harmonic motion means it's a sinusoidal motion. So it's going to be the biggest value is of a cosine is the coefficient amplitude. We just say a cosine omega t. Omega is 2 pi f. 2 pi times 0.166 1.04. So, and we had A is 1.92. And it's in meters. So something like that. Alright, number 7. How long would it take the pendulum to make 5 full swings on the moon? Okay, assuming gravity on the moon is 1.62 instead of 9.81. Alright, so let's just go back to finding t. We have our formula. T is 2 pi square root of L over G. But now we want G of the moon. So it's 2 pi square root of 9 meters over 1.62 meters per second squared. So alright, 14.81 seconds. So 5 times that, 74.0 seconds. Period on the moon. Alrighty. Okay, so the gravity will affect how strongly it's pulled down, how fast it moves. It's not being pulled back so quickly, then it will have a take longer to make an oscillation. So that makes sense. Number 9, assume a constant volume car tire filled with an ideal gas to 45 psi on a cold day of 5 degrees. Assume the tire is 20 centimeters wide, inner radius of 50, outer radius of 80. So we got a tire, something like this. We got 0.2 meters, 20 centimeters wide width of the tire, and then we've got an inner radius of 0.5 meters, and then the whole larger radius is 0.8 meters. 80 centimeters. All right, so what's the volume of the tire? Well, the volume of the whole cylinder is base times height, which is the volume of a cylinder. Cylinder is pi r squared, the base, times the height, right? But then we want to subtract out the volume of the little cylinder, so let's just call this our outer, and then we're going to subtract off pi r squared for the inner radius. So the little cylinder in here we're going to subtract off, and so we can plug that in. So pi and h are both there, and we're just going to have r outer squared minus r inner squared. So pi times h is 0.2 meters, and our outer is 0.8 meters squared, and our inner is 0.5 meters squared. Okay, so we get a volume of 0.2450 meters cubed. Forget the zero. So the big V volume. How many moles of gas are in the tire? Alrighty, so that's a we don't have anything about the mass of the tire or the composition of the gas inside there, and so it must be a ideal gas law type thing. So we got PV equals nRT, and we're looking for N. We got P, where we can convert it, and we got T, we got to convert it. We got volume, so we can get it, I think. So you're looking for N is going to be PV over RT. So P, we want it in pascals. We've got it in 45 in PSI, so 45 PSI. But we've got a conversion here. 1 PSI is 6895 pascals. So the pressure, 45 times 6895. PSI's cancel, we have pascals, 310.3 kilopascals. And temperature in Kelvin is temperature in Celsius plus 273.15. So that would be 273 plus, this is 5, 278.15 Kelvin. Alrighty. We got V, so I think we got everything here. So we got P, 310.3 kilopascals, V, 0.2450 cubic meters, R, 8.1314 joules per mole Kelvin, and T, 278.15 Kelvin. Kelvins cancel. Anything, everywhere. Anyway, everything's in the right units, so we'll end up with moles. So N equals 310.3 times 10 to the third kilopascals times 0.2450 divided by a couple things here in parentheses, 8.314 times 278.15. Alright, 32.87, 32.9 moles. Hopefully you can see all that. back side. If the tire still contains the same amount of gas and the internal temperature rises to 90 degrees Fahrenheit, what will be the new pressure? Okay, in PSI. So 90 degrees Fahrenheit, we want temperature in Kelvin, but we'll get Celsius first. And so we get the conversion 9/5, 5/9. Get the right formula, that'd be good. 5/9 of T Fahrenheit minus 32 degrees. 90 minus 32. So temperature in Kelvin, in Celsius is 5 times 90 minus 32 divided by 9. 32.22. And so then T Kelvin is TC plus 273.15, so T Kelvin equals 305.4 Kelvin. Okay, so we've got T, we want P, we've got the number of moles. So this is again ideal gas law. So PV equals nRT. And we're looking for P now. So we got P equals nRT over V. And N is somewhere. N is 32.87. And R 3.14 joules per mole Kelvin. And T is 303.15. No, 303.4 Kelvin. Divided by the volume, which is 0.2450 cubic meters. Plug it all in, 32.87. .71 kilopascals. We want it in PSI, so multiply by 1 Pascal. Where's my conversion factor? 1 PSI, 6895 pascals. So we're going to multiply. So this is P in pascals. So P 40.71 times 10 to the third pascals times 6895. I already forgot 6895 pascals for 1 psi. Pascals go away, so we're going to divide. So P in psi is 40.71 times 10 to the third divided by 6895. 5.90 psi. New P new. Okay. It's not what I got before. What happened here? got the wrong, one thing I got the wrong temperature, 305.4. Let's try that again, 32.87 times 8.314 times 305.4 divided by 0.2450. Okay. 340.65 divided by that. So that's what I've got here. So divide that by 68.95. I wish I had an eraser that was good. Let's see if this one will do anything. It's better. Alrighty, 49.4. 49.4 psi. Makes more sense because we were at 45. We heated up. It should get higher. Yes. So 49.4. I like that better. What is the average kinetic energy of the gas molecules? Alright, so Ke average is just 3/2 kT. And so T has to be in Celsius, so 3/2 K. Boltzmann constant 1.381, 10 to the negative 23. Units are, I didn't write them down. Let's find those units just a minute. Joules per Kelvin. Okay, that's an easy one. J per K. Yeah, makes sense. Alright, and then we've got to take that off, so multiply by, let's stick it in here, the temperature in Kelvin. So we already have, basically just add 5 to 273, so 278.15. Goes in there, so we got Ke average 1.5 times 1.381 10 to the negative 23 times 278.15. 5.76 times 10 to the negative 21. We got joules per Kelvin times Kelvin, so we got joules, which makes sense because it's kinetic energy. Do I agree with myself? I don't know. I didn't need to do that. I changed that problem, so hopefully that's a good number. Double check that I've got it in the calculator right. I think so. Alright, what is the total kinetic energy of the gas at 90? Okay, so Ke total. So now this is for all of the molecules. And so this is going to have a, either, it's going to be N times 3/2 kT. I don't think we have N, so we can also use little n times R. 3/2 number of moles times R times T. Yeah, let's use that one. And so 3/2 N was 32.87 mole. R is going to run out of room again. 8.314. That is joules per mole Kelvin. And the temperature at the 90 degrees is the 305.4 Kelvin. Alright, so Ke total, plugging those in, 1.5 times 32.87 times 8.314 times 925 kilojoules. That's what I got last time, so that's good. And then finally, number 9 part F. If some of the gas molecules are O2, how fast are they going at the 90 degrees? Okay. I should have done it at the... So we got the kinetic energy average. Well, we can just use the formula. So VRMS, we don't have to use kinetic energy. We've got a formula for VRMS directly. Two formulas. Which one do we want to use? Got 3RT over MA. Or 3KT over M, but we haven't calculated M. So let's use MA. So we've got 3. R is 8.314. Joules per mole Kelvin. And then the temperature in the 90 in Kelvin, 305 Kelvin. And the molar mass of oxygen is 32 grams per mole, so 0.032 kilograms per mole. Alright, so the moles down there cancel, the K's cancel. Anyway, we got kilograms and joules, but everything's in standard units, so we'll end up with meters per second. VRMS is square root 3 times 8.314 times 305.4 divided by 0.032. 488 meters per second. Velocity of the oxygen O2 molecules. Alright, I think that will do it.